Now, let us consider motion on an inclined plane. Let us now consider various problems in which a block rests on a surface inclined at an angle theta to the plane. Now, we will consider 6 simple cases with a block resting on the plane. Let us obtain expressions for the value of the force P acting parallel to the plane. First, to hold the body at rest, to pull the block up, and to pull it down. Then let us repeat the problems with the force P horizontal instead of parallel to the plane. We shall gain more insight if we solve these problems in algebraic terms rather than arithmetical substitutions. The force P is the haulage force required in each case to move the block in the required direction. When the force P is parallel to the plane, there is no advantage in using the angle of friction. And so the 4 forces PW, Rn, and Urn are shown separately. Now we have here a force parallel to the plane of motion. 1. Body held at rest on plane by external force P parallel to the plane. Now, if we assume that this body is held at rest by this parallel force P, now, if I resolve the force diagram this way, now I will consider this as the weight acting downwards. Are we there? Now the body is on top of the plane. This will be the normal reaction acting upwards. Are we there? Now without this force P, this body will slide down. So the force of friction will act in the opposite direction. Let's call it mu Rn. Are we there? Now if I resolve the weight into 2 component directions, one parallel to the plane and the other one vertical to the plane, I'll call the parallel direction as W sine theta. Mark you this angle is theta. Now I'll call this W cos theta. Are we there? Now let's see. Now this is the first diagram. Now let's resolving the system of forces, the forces parallel to the plane, parallel to the plane. What do we have? Now we have W sine theta moving towards the left is equal to P plus mu Rn. We have W sine theta equals to P plus mu Rn. Let's call this equation number 1. Now let us resolve horizontal, the vertical to the plane, right? Resolving the forces vertical to the plane. Are we there? We have the normal reaction acting upwards equals to W cos theta acting downwards. So we have Rn equals what? W cos theta. Are we there? Let's call this equation number 2. Are we there? Now we have force P in which we are looking for. We have the normal reaction, right? So if we make the normal reaction as the subject of this formula, then we substitute equation 2 in 1. Now, I put down sub 2 in what? In 1. In 1. Are we there? We have W sine theta is equals to P plus mu Rn. What is Rn? Mu W cos theta. Are we here? So I'm going to make P the subject of this formula. So I will have P is equal to what? W sine theta, right? Minus mu W cos theta. Are we here? So W is common. I will factorize W. So I have P is equal to W open bracket sine theta minus mu cos theta. Therefore, the force P required to hold this body on an inclined plane is P is equal to the weight into sine of the angle of the plane minus the coefficient of friction multiplied by cos theta. Now let us consider the next case, direction of motion up the plane, holding force P parallel to the plane. Now let's see. This is the inclined plane, alright? This is the body, the body, alright? And the direction of motion is up the plane. So I'm going to put the force P trying to move the plane, the body up the plane. Mark you, the plane is inclined at an angle theta, alright? Now, I'll have a normal reaction like this. Normal reaction acting upwards. They will have the weight of this body acting downwards, alright? Let us call it W, alright? Now, if I resolve the weight into two component parts, I will have this as W sine theta, and I'll have this vertical direction as W cos theta, right? Now, the body is trying to move upwards, so the force of friction will act in the opposite direction, which will be mu Rn. Now, this is a system of forces acting on this body. Now, let us again resolve the system of forces. Either, let's say, horizontally, right? We'll have what? P going upwards is equal to what? Mu Rn, right? Mu Rn plus what? Plus W sine theta acting in the opposite direction. What I mean is this: the force P is pulling this block upwards. Now it's being opposed by the force of friction, mu Rn plus W sine theta, the component of the weight acting parallel to the plane. Are we there? So let me call this equation number 1. Then we resolving the system of forces, parallel to the plane, or vertically, alright? Now vertically, we have Rn, the normal reaction, acting upwards, which is being opposed by W cos theta. So I would say Rn, right, equals to what? W cos theta, alright? Let's call this equation number 2, alright? Now let's see. Equation 1 says P is equal to mu Rn plus W sine theta. While equation 2 is saying Rn is equal to W cos theta, alright? Let's substitute equation 2 in equation 1. equation 1. Alright? We'll be having P is equal to mu. What is our Rn? Mu Rn. What is our Rn from here? Rn is equal to what? W cos theta plus what? Plus W sin theta. W sin theta. Again, W, that's the weight, is common. So I'm going to factorize that. That will give us P is equal to W into bracket mu cos theta plus sin theta. Therefore, for a force trying to move a block up an inclined plane, the force required P is equal to the weight into the coefficient of friction multiplied by cos theta plus sin theta. Now let's consider the direction of motion down the plane while the hauling force P parallel to the plane. Now if I draw the inclined plane this way, right? And I put the body here, okay? The angle of the plane, remember, is theta. Are we there? So the normal reaction will act this way, alright? And I put the normal reaction as Rn, normal reaction. Are we there? The weight of this body will act downwards. Let's call this weight W. Are we there? Now if I resolve the component of this weight into two component directions, I will have the one parallel to the plane as W sin theta. Marking this angle is also theta. Alright? Now, the component of the weight acting downwards, alright, will be W cos theta. Are we there? Mark you, the force P is trying to pull the body down the plane. So I'll represent this force by P. Now, the force of friction opposing P will act up the plane, which will be mu Rn. Are we there? That gives us the system of forces acting on a body, right? On a plane where the pulling force or the hauling force is P acting downwards. Now let us resolving the system of forces. Now let's say horizontally, right? Horizontally. Alright? Let's see. We have force P pulling this body downwards, and we have W sin theta also pulling the body downwards, which is the component of the weight acting in the horizontal direction. These two forces are being opposed by the force of friction. So I can write P plus W sin theta equals what? Mu Rn as our equation number 1. Are we there? Alright? Now, resolving the system of forces vertically. Are we there? Now, the vertical forces are the normal reaction acting upwards and the component of W cos theta acting downwards. So I can now balance these two forces as R n equals what? W cos what? Cos theta. Now let us call this equation number 2. Now, equation number 1, P plus W sin theta equals to mu R. And I have equation number 2, Rn is equal to W cos theta. So let us sub equation 2 in what? In equation 1. So we have from equation 1, P plus W sin theta equals to mu What is Rn? W cos theta. Okay? Let us take the W signs to one side so that we make P the subject of this formula. Therefore, we have P equals to mu W cos theta, right? Mind, please, it is plus here. So when it goes to the other side, it becomes minus W sine theta. Are we there? So we have W common here and W common here. So we can factorize. That gives us P equals to W, you open bracket, mu cos theta minus sine theta. Therefore, if we have a body placed on an incline of angle theta, and we're having a force P parallel to the plane, intending to pull that body down, the force P is given by W, open bracket, coefficient of friction, multiplied by cos theta minus sine theta.